Okay, good morning, everyone. We come to lecture 18. So today we'll talk about the adiabatic approximation and the Berry phase. The adiabatic and Berry phase. So the Berry phase and all Berry curvature, they are significant quantities in solid state physics. Okay, so for example, we all have heard like quantum Hall effect, topological insulator, like those are all related to Berry curvature. Okay, so but usually in a normal quantum mechanics courses, even in the graduate level, they don't teach Berry phase or Berry curvature. So here I hope through these lectures we can learn it together. Okay, I have learned it before, but I can also review this together with you all. So the Berry phase is related to something called the adiabatic process. Okay, so let's first talk about the adiabatic process. Sorry, let me double check whether the phone is open or not. Okay, it's okay now. Okay, so we come to lecture 18 on the adiabatic approximation and Berry phase. So let's first talk about what is an adiabatic process. Basically, you can just understand adiabatic process as a very slow process. Like how slow? Just very slow. So slow that you can make the limit of very slow. The time scale is longer than any dynamical time scale of the system. Okay, so let me give you an example. Let's say you have a pendulum. Okay, you have a pendulum. And you have a pendulum. Okay, so the pendulum is oscillating. And we know that, let's say this L is length. And we know that the period for the pendulum is 2 pi L over G. Okay, you can do this calculation just from classical mechanics. So suppose now I can change the length. I can change the length of this pendulum. Okay. Suppose L becomes L as a function of t. That means when the pendulum is oscillating, you actually let the length changes. I think this is slightly shorter. Okay. And then what is the dynamics of the system? Okay, what is the dynamic of the system? So if the change is very slow, the change is very slow. How slow? Like much longer than t. Like you let this L change very slowly, and the time scale is much longer than the period of this pendulum. Then the new period is presumably t also as a function of t equal to 2 pi L as a function of t. For example, this pendulum is oscillating once every 1 second, but you are changing the length of this string in the scale of 1 day. Okay, in 1 day you change it slightly. Then you can see that the period of the pendulum just depend on the instantaneous length of the pendulum. Okay, so this is an example of an adiabatic process. So the time scale is only compared to the dynamical time scale of the system. How long is called long, how slow is called slow. You compare that with the oscillation of the pendulum. Okay, but if the pendulum oscillate as a period of 1 day, then if you change the length in 1 day, then it's not long enough. You probably need to make it 1 month or 1 year. Okay, so whether it's very slow, whether it's slow or not, is in comparison with the dynamical time scale of the system. Okay, if you are considering oscillation in atomic scale, then 1 second is already very long, very slow. Okay, so another example, example 1. Okay, example 1. So this is one example. We'll use the pendulum example later. Okay, so example 2. Example 2 is when you have a quantum well. Okay, you have a quantum well. So this time we use a quantum mechanics example. So there's a ground state here. Okay, there's a ground state. Okay, so this wave function, the initial wave function, let's say this length is a. So this is a quantum well. So this is the wave function. So this is 2 over a sine pi over a x. So that is the wave function of this ground state. Okay, now we allow one of this wall to be able to move. Okay, we allow this wall to move very slowly, Okay, so you just let this, let it draw it better. Okay, you just allow this wall to move, move slowly. Okay, then at every instance, this wave function will just follow. Okay, so at every instance, so here, you can have this the final state will be equal to this a. This a will be a function of t. Okay, so this a will be a function of t. Okay, it's moving very slowly. Okay, so then you just have a as a function of t, and this is also as a function of t. But you need to move slow enough. Okay, if you don't move slow enough, then what will happen? If you don't move slow enough, then you will. If you move suddenly, then this is what happens. If you move suddenly, then the wave function won't change at all. If you just move, suddenly, then the wave function won't change. It cannot respond. So you just get exactly the same wave function. And this is no longer an eigenstate of the new quantum well. So this is not the eigenstate, but this one is an eigenstate of the new quantum well. So whether it is not adiabatic or not adiabatic is determined by whether the system can respond fast enough to your change. If the system can respond fast enough, the system will just follow your change. You go to a new system, then this wave function is still will evolve into the new eigenstate of the new system. If this can happen, then we call this an adiabatic process. Okay. So these are two examples of adiabatic processes. Okay, so now we come to this adiabatic theorem. And then we're going to prove it, okay? So what is an adiabatic theorem? It states that, if a particle was initially in the nth eigenstate of this initial Hamiltonian, it will be carried into the nth eigenstate of the final Hamiltonian under the adiabatic process. Or maybe I can say this. If Hi evolves into XF slowly. Okay, here we just assume the spectrum is discrete and non-degenerate. Throughout the transition. Throughout the transition. Okay, so this is the adiabatic theorem. This is the adiabatic theorem. So let me go through this again. Okay, if a particle was initially in the nth eigenstate of the initial Hamiltonian, it will be carried into the nth eigenstate of the new Hamiltonian, HF. If this HI evolves into the HF slowly, means very slowly. Okay, how slow? It is much slower than the dynamical time scale of the system. Okay, basically you can make the approximation of time equal to infinity. Okay, and we assume that the spectrum is discrete and non-degenerate. Okay, so we're going to prove this theorem. And then the Berry phase will come out in the proof. Okay, then that is how we know what the Berry phase is. Okay, so So let's assume, okay, let's start from, okay, let's go with the proof. So if, okay, for time independent Hamiltonian, okay, and the particle is in the nth eigenstate, then we have this Schrodinger equation for this eigenstate. Okay, so we learned this already. It's nothing new. So this wave function depends on time. Okay, and it is let me see. This is a big phi. Okay, this, and then this is the small one. Then you pick up a phase factor. Okay, so this is the result. Okay, so now let's consider. So if Hamiltonian depends on time, then for each time you have the Hamiltonian t, and then for then this one will also be an eigenfunction. So for every time, every value of time, you have a new Hamiltonian h depend on t. Then at that particular moment, you solve the Schrodinger equation, you will get a new eigenenergy and a new eigenfunction. Okay, so it's just the same as this, except that now you consider changing Hamiltonian with time. And at every time, you have a new basis. Okay, so this eigenstate will form a new basis. Form a complete basis. And you have this orthonormal relationship. Okay, you have this orthonormal relationship. Then the time dependent, Schrodinger equation is I, and then you have this. Okay, now this one at any time can be expressed as a linear combination. Okay, as a linear combination of this new basis. Okay, at a certain time. Okay, so the coefficient is Cn. It depends on t. This is a small phi. Okay, small phi, and then with a factor, a phase factor. So this phase factor is defined this way. Okay, so let's try to understand what is going on here. Okay, let's try to understand this. Where? Okay, so we want to solve this Schrodinger equation at a particular time t, and then because this new eigenstate at the particular time t, they form an orthonormal basis. So you can always express this general wave function as a linear combination, of this basis, okay, of this basis, and you will have a coefficient. So in principle, you don't need this, thing, okay? In principle, you just write it in like this, that is already good enough, okay? All the phases, all those things are already included in this time-dependent factor. But we know that there's a particular part that is due to the energy. Because generally, every wave function, the eigenfunction will evolve according to this phase factor. Sorry. Yeah, negative. Yeah, mistake. Okay. Thank you for the correction. So this is a dynamic phase factor. Okay, so this is a dynamic phase factor. This is a dynamical phase. I mean, it's nothing special about this phase. So, and we want to exclude this phase in our consideration. So that's why when we write down this coefficient, we just take the dynamic phase factor out. The dynamic phase factor out. Okay. And because now the energy is changing with time. So it is not a constant. So we just do an integration. Okay, so every time you integrate over this E, then you have this dynamic phase factor, and we take it out. And we only consider the part that does not include the dynamic phase. Okay. So now we're going to plug this into here. Okay. So let's say this is 1 and 2. Okay. So let's say this is 3. Okay. We're going to put 2 into 1. Okay. You're going to put it into here. So you have the time derivative. So let me copy this. Then you have this thing. And then you just do a derivative. This whole thing. And then you have the Hamiltonian. And also this whole thing. Okay, so let's do it on the first part. We're going to use a dot to represent the derivative. Okay, you use Cn dot, and then we're going to neglect the notation of time and Cn. So you do a derivative here. You just use the product rule. Okay, and I use a dot to represent the derivative, and then you're going to use Cn, and then you're going to do the derivative here. So when you do the derivative here, what you will get is you're going to bring the I inside, and then you bring the theta back, and then you have a dot. Okay, so then you have this phase factor here. So basically just a product rule and nothing special. You do derivative here, do derivative here, do derivative here. Okay, so when you do a derivative here, you just bring this factor down, and then with the derivative I'm fine. And then all of them share the common phase factor, so I'm going to put it here. Okay, so this is on one side. And then on the other side, you're going to have Cn, and then your Hamiltonian is going to be here. Okay, because the Hamiltonian will only operate on this part. The other things are just constant parameters. Okay, so you have this. Okay, so that is the new equation. Okay, so then let's see how this is going to operate. Okay, so this one is going to bring En. Of course, this En will be En as a function of time. Okay. And then what is this theta? Okay, this thing, theta n equal to this thing. And then have a derivative on t. Okay, so, and this is the integration. So after you do the derivative, you just get t. You just get t. Okay, so eventually, this whole thing will become, let's do it one by one. Okay, just separate it then. What do you mean? Yen, because there's an n here. So this is n. Okay. So yeah, sorry for the notation confusion. Okay, so we're gonna separate them one by one. Copy. Is it one? Maybe just I just feel it's too many things. Let me separate them term by term. Okay. Okay, so here Cn, you have an I, and then with this thing, -1 h bar En, and then equal to n Cn, I mean this part, and then En. Okay, so for this one, you can see that this and this got canceled out. Okay, got canceled out. So eventually you just get Cn phi n En omega n. Then eventually you find that this part and this part are canceled. Okay, are canceled. So eventually only this part is remaining. Okay, and then it's easy. You can cancel this one. Then eventually you get this thing and this thing. Yeah, okay. Eventually you get something like that. So this is so far we haven't made any approximation. No approximation. We're just solving the Schrodinger equation and just writing the Schrodinger equation in terms of this expansion coefficient. Basically, if you solve this expansion coefficient, it's equivalent to solving the Schrodinger equation. Okay, so the typical strategy is going to remove this summation. Okay, so we're going to take the inner product with this M. Okay, so you're going to have times here. So basically, you're going to get this thing. Of course, if you use the cat, then you make this a bracket notation. Okay, so and then for this one, you move the n outside. You don't need complex conjugate. It's already the bra state. And then this one will be delta mn. Then eventually this whole thing will be just Cm E phi m. Okay, so then you just move this phase factor to the other side. Then the Cm will be negative. Sorry, I missed one. Is this here? Okay, so now you can add the time dependence. Okay, you can add the time dependence. Of course, all of this this also depend on time. Actually, even these wave functions, they're all time dependent. Okay. So this so far we still haven't made any approximation. We're basically just rewriting the Schrodinger equation in terms of the expansion coefficient. Okay, so now let's go back to this equation. This equation, okay, copy. Okay, differentiating. Gives, okay, you do the differentiation on this. Okay, so you do this. By the way, all of these are time dependent. They're time dependent. Probably I copied the time independent equation. But anyway, I intended to. But anyway, here we're using the time dependent equation. Okay, so you're going to after you do the derivative, you're going to get this. Okay, and here you have En and En. Okay, then take the inner product. Then you have this. Huh? And then with En. Okay, so now let's see. This one, you apply the Hamiltonian on the brass state. On the brass state, then you get Em. Okay, so this one is just the delta function. Okay, so eventually you get this one equal to this thing minus this thing. Okay, so En minus Em. For m not equal to n. So we only consider m not equal to n here, so that this term is 0. Okay, so we're going to use this result. We're going to use this result because here we can express this as this thing over this thing. Okay. Of course, this condition carries on. Okay, so now let's go back. Let's go back to here. Let me see, equation number 1, 2, 3. Let me say this is let me say this is 4 then. Okay, so this is 5. Okay, so putting 5 into 4. Okay, so this is 4. So this one can be expressed as, you first take the term m. Okay, Cm. Then once this equal to m, and then minus n not equal to m. So we're going to separate this summation into the m term and the m not equal to n not equal to m term. So for this term, we just copy this thing. Maybe. Anyway, when this is equal, this is 0. Okay, so we can actually delete this phase. Okay, so this will save us some space. Okay, then I'll put this here. Okay, Okay, so now we can use this result. We can use this result. We can use this result. Yeah, we can use this result. Huh. So eventually, you will take this part and minus and then Cn and copy this thing. Make it somewhat smaller. You don't need the parentheses here. And then E, I, N, and M. So what is this? So let's recall. Let's recall what theta is. What is theta? Theta is this thing. Copy. Okay. We recall. Recall theta is this. So from this one, you write this. I need to make it somewhat smaller. Okay, so you're going to put this in. You're going to put this in. And then you're going to have a E negative I H bar. And then you're going to have the integration. En minus Em. And then d derivative. Just put this definition into here. Okay, into here. Then you get this answer. Okay, so this result is exact. We haven't done any approximation so far. This is still the Schrodinger equation, just expressed in a form in terms of the expansion coefficient C. We haven't made any approximation. So here comes the adiabatic approximation. Okay. Okay, we're going to assume that it is extremely small. Extremely small. And drop the second term. Let me say this is equation 6 then. Is it 6? Okay. In 6. Okay, we're going to drop this term. We just assume it is very small. Actually, the rigorous justification of this step is not trivial. If you want to rigorously show that you can really drop it in the adiabatic process, I think you need further proof. Okay, but the textbook only give a citation, so we'll just take it. Okay, we're going to neglect this term because this is h dot is small. You just make it very, very, very slow and take this to 0. So you only have the first term. You only have the first term. So the adiabatic approximation basically reduce the Schrodinger equation into a simple form. Okay. So 6 is approximated as is reduced as this. So this is just a Schrodinger equation with the adiabatic approximation. So this is the the Schrödinger equation with the Adiabatic approximation. And this one can be solved. This one can be solved. So how do we solve it? The solution is CMT equal to CM0. This is the initial condition. And then with the phase factor gamma MT. So what is gamma? So gamma equal to I T prime. And then delta T. So you see that there's no coupling between different N and M. Okay, there's no coupling between different N and M. These are all M. These are all M. The summation over coupling with the other eigenstate, they disappear with the adiabatic approximation. So basically, with the adiabatic approximation, every eigenstate evolves into a new eigenstate without mixing the other. Okay, so you only have an M here. So and this one can be solved because basically it's just a derivative equal to the original function times a certain factor here. So the solution has this exponential form, and you can put this into here and do the derivative, then you'll find that this is the solution. Basically, when you do the derivative here, you take down the phase, okay, and then you can just confirm it, okay. When you do the derivative on this one, and then you remove the integral, and then this part just come out, and that will become this constant. Okay, so that is the solution. Maybe you can just simply confirm it. Okay, so copy. Okay, so let's do the derivative. Then this will be the derivative. So this one will be I M dot T. Okay. And then this derivative here would just give you I. Okay. Okay, so then this just become negative. Okay, so and this one can be put here. And then this one is just Cm. So you have negative Cm. Okay, so eventually you get this, this is just the original equation. Okay, so this proves that this is the solution. Hmm? It's already I. 2I? Which one? Which step? Here? Solution. This one? Why there's an I?
It's like E, gamma, and minus one.
Why do we need to add I here? You don't have to, because once you put the I here, then here you need to have an I.
This step is
You feel it's a bit redundant? Later you know. It's just a convention. Because for phase factor, you usually take the I out, and this will be the phase. Okay, and okay, so once you solve this, okay, we're going to plug it in to the original equation. Okay, so we have to go all the way down, up here. Okay, here. Okay, this is equation 2. This is the eigenfunction. This is the eigenfunction. Okay, so copy equation 2. Okay, recall. Equation 2. Okay, so let's assume if Cn0 is 1 and Cm0 equal to 0 for m not equal to n. So that means that is the particle starts out in the nth eigenstate. Okay, if the particle starts at nth eigenstate, then initially it will be just in n. So initially it will be just in n. So you just type it as n, and then you just remove this. Okay, so initially this here. Okay, so this thing will be this. This one will be this. Of course, you need to change all the m into n. And then eventually you get the wave function at any time. The wave function at any time will be. And this is 1. And this is 1. Okay, this is 1. This is 1. Okay, so you will have E I phi n and E I gamma, and then you have phi n. Okay, so this is the solution. That means if you start out with only in the nth eigenstate, and after a long time, the new eigenfunction will have this form. We have this form. It remains in the eigenstate. It remains in the nth eigenstate with 2 additional phase factors. Phase factors. So this phase factor is the dynamic, is the dynamic phase factor. Basically equal to I, equal to you just recall it. This one is is the dynamic phase. So this one is nothing special. It's just the energy part. Okay, when you have the energy, then you always have a phase follow it. And this is the additional phase. So this is the additional phase. This is the additional phase. With two phase factors. Okay, so this will be related to the Berry phase. Okay, this will be related to the Berry phase. It's okay. So we're done with the proof. We're done with the proof. Any questions before we move on? Okay, what's your question?
From the equation 2, so how to get from the linear combination?
Because you assume that the particles start out in the nth eigenstate. So at the beginning, this is 1, and all the others are 0. Okay, all the others are 0. So because you start from 0, so all the components in the adiabatic approximation, if it is 0, if this is 0, then it remains at 0 all the time. So you only have one eigenstate all the time. So that means, so I mean, I can, so that means Cn T is 0 if n sorry, I should use m. If m not equal to n. Because of equation, because of this. Okay, because of this. Because of make it small. I mean, I can insert the explanation here. Okay, is this enough explanation? Because they evolve according to this equation. If initially it is 0, then it's always 0. It's 0. So that means this thing, you can decompose it. You can decompose it into, just write a few more steps then. That's for the sake of completion. For the sake of completion, just write a few more steps. So just has this one, and then plus these are all m, and then this is m not equal to n, and then this is 0. Okay, so then you have this term. Okay, so that's clear. That's clear. Oh, where does it go? Okay. Okay, so we're done with the adiabatic approximation. Sorry, adiabatic theorem. So basically, the theorem basically says that if your Hamiltonian evolves very slowly, the new eigenstate will be the same as the initial eigenstate, but it will pick up two phases. One is just the dynamical phase, and the other is an additional phase. And this additional phase is what we're going to focus. And this is what we're going to focus. Okay, so this additional phase is actually measurable. Measurable. That you can devise some experiment to measure this additional one. This additional one. Okay, do you have any questions before we move on? Okay, now let's continue. Okay, let's continue. So we're going to talk about the Berry phase. So suppose so we start from I just start a new page then. Okay. Berry phase. Okay. So now we start with this. You have this wave function. Okay, this is what we got before, and there are two phase factor. And then so this one is the dynamical phase. Is the dynamic phase. This one is actually called the geometric phase. The geometric phase. Okay. This. Okay. Okay, we're going to start with with here. This is the dynamic phase. This is the geometric phase. Okay, suppose H phi t depends on t, on time, through another parameter called RT. Let's say your Hamiltonian has some parameter, and that particular there's one parameter that depends on time. So your Hamiltonian is a function of R in terms of function of t. Okay, so this is the parameter. Suppose there's only one. Suppose there's only one parameter. Okay, just one parameter. Okay, just one parameter. Okay, so let's get this thing. Okay, so let's get this thing. So this one will equal to this derivative will be dr, and then you have the dr over dt. You use the chain rule. You can change this into r. And then this is from 0 to time, right? So you can change it to initial to final r. Okay, you change the variable. Okay, you change the variable. So this will be dr. Okay, I mean it's just some calculus change of variable. Okay, so now let's consider some particular case. If RF equal to RI, then this is 0. This is 0. There's nothing interesting here. There's nothing interesting. Basically, you go through like let's say you have a R initial, and then you go here, and then you just go back. You just move all the way and then move back. Then this will be 0. Nothing interesting happen. Okay, the interesting happens when you have more than one parameters. Okay, so consider but if there are more than one parameter on time. For example, R1T, R2T, R3T. Okay, so let's say the totally n parameters, Rnt. Then this derivative, Tn, will be, you need to decompose it into R1. And then R2. You just dot. Okay. And we know that this is just the gradient. Okay. You take the gradient of R, and then N. Then this R will be a vector. Okay. Then you have a dot product, dr vector. Okay, dr vector. Okay, so then this geometric phase here, okay, this thing will be modified. This one will be modified. How do we modify it? You're going to have this thing become the gradient of R. M. And then this one will be M. And then this will become a dot product. Okay. So then eventually you're going to add the arrow here. Okay. So this one will become just dr. And then the initial to final time eventually will become from initial I to final I. Okay. I mean you can call this as a vector. Okay. Let me So R1, R2, R3, they don't have to be the same type of quantity. They can be just different type. Is also fine. That you just artificially make them into a vector, just for the sake of the simplicity of notation. Okay. So R1 and R2, they can be different type of parameters. Okay. So after that, you have this. Then what is this? This is a path integral. So this is a path integral. Okay, so this is not path integral, it's a line integral. Okay, don't get confused with the Feynman's path integral. Okay, this is a line integral. That means the result depends on the line. Okay, the result depends on the line. For example, let's say you have let's say you have two of them. Okay, let's say you have R1, you have R2. Okay, let's say you have two parameters. So if you have a Ri initial, then you make a loop, and then you go back to Rf. Then the integral is on this loop. It's on this loop. Okay, it's on this loop. Okay, so if Rf equal to Ri, then this one will become a closed loop integration. This gamma. It will be a period. It will be a period. After a time t, then this one will become a closed loop integral. Will become a closed loop integral. Sorry, I forgot to change this into a gradient. Copy. Okay. Okay, so this is called the Berry's phase. The Berry's phase. And first obtained in 1984. In 1984. By Michael Berry. So this one is a kind of a relatively recent result, like not like those early quantum mechanics result that are in the 1920s or 30s. This one is the 80s. So it's like relatively recent. But you can see that the whole derivation process is nothing like a very technical. It's just a Schrodinger equation. So it's actually interesting that even after so many years of the Schrodinger equation, you can still like derive something new from there. Okay, so let's consider a 3D case. Let's consider the 3D case. What is the 3D case? The 3D case is when R equal to only R1, R2, and R3. So only 3 of them. Then this one, will be according to the Stokes theorem. We can use the Stokes theorem. Stokes. To write it as, so basically write it as the curl. Okay. The curl. The curl of this thing. And then will be dot dA. And this is what we call the Berry curvature. I think this is the Berry curvature. So basically, the Berry curvature is this middle part. You take a curve. You take a curve. I'm not sure whether the Berry curvature include the eye or not including the eye. Okay, I'm not very sure, but anyway, it's just the curve of this thing. So basically, you change this line integral into a surface integral, Is okay? So that is the definition. So we're going to do an example to calculate the Berry phase or Berry curvature. Okay. So I am going to give you two examples. One is classical. The other is quantum mechanical. Then we're done with the lecture. Okay. So example. Okay. Example of geometric phase. 1. So there are now Berry phase is a one type of geometric phase. Okay. Basically, what do you mean geometric phase is when you make something go in a loop, then you have a similar state and pick up with a certain phase. This is called geometric phase. It does not depend on how, but as long as you move slow, then you only depend on the geometry of the process. And Berry phase is the geometric phase in quantum mechanics. But but geometric phase also exists in classical mechanics. And one example is the pendulum. There's something called the Foucault pendulum. So do you notice that the physics department has a Foucault pendulum? In the ground floor, there's a pendulum. Do you know what this pendulum is used for? Have you ever observed it? Yeah. This is actually a proof that the Earth is rotating, and also from there you can actually know the angle of Riverside, like where we are in the angle of the globe. So how do we do it? So let's consider the globe. This is the Earth. Okay. So, and then, okay, this is our equator. Okay, this is the equator. So let's say you have a pendulum that is oscillating in the North Pole. Okay, let's say this is the North Pole. Okay, it's oscillating. and it is oscillating along the direction of here. Okay. Then we're going to move this pendulum along this path slowly. Okay. So at every point, you can imagine that the pendulum is going to oscillate like this, right? You just keep moving. So when you move this into the equator, you can imagine that the pendulum is oscillating like this. Okay. You do it slowly. So first you do it like this, and then second you move it like this. Okay. So at every point, so let's say you move it to here, then the pendulum is going to oscillate like this. Okay. Just follow the equator, and then you move it back. You move it back. Okay. So after you move it back, so in the whole process, it's still going to oscillate like this. But after you move it back, you'll find that it will rotate for an angle. I mean, this is easy to imagine, right? You have this, first is this, you have a plane like this, and then later it's going to be rotate. Okay, so if you look from the top view, at the beginning, you're moving like this. Okay, so after you come back, it is going to oscillate like this. Okay, so what is this angle? This angle is this theta. So this angle will be the theta. Okay, this theta is the geometric phase. Is the geometric, should I call it phase or angle? Yeah, it's something related to geometric. It's an angle. Okay. Angle then. Okay. Okay, so you pick up something, some rotation. Okay, when you have a rotation, you have a phase, right? Okay, you pick up this, and you'll find that this angle is the same as the solid angle of the enclosed area of the path, of the closed path. Of the closed path. That is this part. This part has a solid angle. That solid angle is the same as the rotation. Is the same as the rotation. So how do we know that? You just do the calculation. What is this? This one. So what is this area here? Okay, so let's this area. Okay, so this area. So this area A. Area A equal to first, the whole surface is 4 pi r squared. So this is the surface area of a sphere, and you take 1/2 of it because you only travel by 1/2. So take 1/2, and then you are taking a fraction of this angle, and if you make a whole round, right? If you make a whole round of it, it will be 2 pi. It will be 2 pi. Okay, so you cancel this 4 pi here, then you get this theta r squared. So what is the solid angle? The solid angle is this area over r squared. So this is the definition of solid angle. So this is theta. Okay. So suppose now, okay, you are not doing something this regular. Suppose now you are doing something irregular. So let me consider another case. Just for example, let's just consider the pendulum in Riverside in our physics department. Okay, suppose we just consider the Foucault pendulum in the physics department. So let's define the center here. Okay, so let's say this where's the center? Okay, here. Okay, let's say this is the z-axis, and then this is the x, the y, and then let's say where's Riverside? Okay, around here. Okay, let's assume it is here. Okay, let's assume it is here. So what is this angle? So this angle, let me call it theta 0. Okay, so let's say this is Riverside. Okay, you're having a pendulum here. So now instead of moving the pendulum around, the Earth is rotating, right? So the Earth will carry the pendulum to move around. Okay, and then this pendulum will pick up a phase after the Earth rotate for one round. Okay, like today, 12 o'clock, you look at it, you go back tomorrow at exactly the same time, you find that this focal pendulum will rotate an angle. Okay, next time you can pay attention. You go to do the TA, like 12 o'clock, you go there, take a picture. Tomorrow, exactly the same time, you go back to take another picture, you'll find that you rotate for an angle. And that angle will tell you this angle. You will know the position of Riverside on the Earth. Yeah, okay, so let's get the solid angle. Now you are making an adiabatic process. The Earth carry the pendulum and go through one loop and go back to the same position. Okay, that is an adiabatic process. The period is 1 day, but your oscillation is much faster than 1 day. Okay, so that is a adiabatic process. Okay, so I mean, I actually never did it. I never observed it. Maybe I should do it. Okay, like it. I think it would be interesting observation. Yeah, of course, the Earth is rotating. So you just know this angle. Okay, so anyway, so let's solve the solid angle. Okay, we have a solid angle. So what is the solid angle? So this, I mean, we just simply do an integration. Okay, we just simply do an integration. Okay, you have a small part, this part. Yeah. Okay, this part is R d theta. Okay, this is R d theta. So this area is, this whole thing is R sine theta. So this length, this is R sine theta. Okay, R sine theta times R d theta times R d theta. Okay, this is the radius. You have 2 pi times it. That will be the whole length of this thing. And then times this part, that will be the D area. Okay. So this will be the D area in this small part. Then you are going to do an integration from 0 to theta 0. Yeah. So then you get the area. You get the area. So how do we do it? 2 pi r square. So this is just a negative cosine. And then theta 0. So this will be cosine theta 0 minus cosine 0. Cosine 0, just 1. Okay, just 1. So you get 1 minus cosine theta 0. Okay, so the solid angle is this over r square. So it will be this one. Over r square. So that means it will be 2 pi 0. So this will be the angle. The rotation of orientation of the Foucault pendulum. This is Foucault is a French name. I checked the pronunciation in English, and it's called Foucault. You don't need to pronounce this T or L there. Just Foucault. Foucault pendulum is theta equal to this, and equal to this. Yeah, maybe I give you an assignment. How about you just go and check this angle and tell me in the next lecture. Yeah, each one of you, when you go to lunch, go there and take a picture. Next day, go to lunch, and exactly the same time, go and take a picture and get this angle. I think it would be kind of impress you about what the geometric phase means. Is that okay? I think that would be an easy assignment, right? Okay, so this is geometric phase. And you can generalize this to more. Basically, this path doesn't need to be circular. If you take a path like this, like a very irregular path, you get exactly the same thing. The rotation will be just the solid angle. You can make the path as irregular as you want, as long as it's a closed path. Then you get this area, and then get the solid angle. Then that will be the rotation of your pendulum. Okay, so this is the simplicity of geometric phase, because it does not depend on the exact path. It depends only on the area. So this is an interesting thing about that. Is it okay? Okay, so now we're going to do a quantum mechanics example. Quantum mechanics example of this geometric phase. And you will have, of course, eventually we'll go to the solid state and see how the Berry curvature will affect the properties of a material. Okay. So example 2. Example 2 is on the electron spin. And a rotating B field. Okay, and the rotating B field. Okay, so suppose you have a B field. Okay, let's see. Okay, suppose you have a B field. You have a B field. Let me see. You have a B field that is rotating. Okay, so let me see. So you have this angle is called alpha. Okay, a fixed angle with alpha, and then the B field rotates along the z-axis with a velocity, with a angular speed omega. So that means this B field is going to rotate like this. So basically the B field is like this, rotating. Okay. So your Hamiltonian will depend on the B field. So what is the Hamiltonian in this case? This is like one of the simplest example. So your Hamiltonian is this. So this B field, you can write it as a function of time. As a function of time will be B0 and then sine alpha cosine omega t. And this will be the x and then sine alpha omega t. This will be y. And then this will be cosine alpha z. You just decompose it, okay? You just decompose it into the x and y. Okay, you can go down and then you can just rotate. So this will be omega t. Maybe I should write it like this. Not. Maybe I should write it like this. Okay, and then okay, so this one will be omega t. So you just decompose. The cosine part will be the x, the sine part will be the y, and then this will be the sine alpha. Okay, I don't think it's that difficult. Okay, so you just write the B field, and this B field rotates after one revolution, then we just go like this, omega. Okay, just go like this, omega, rotating. Okay, what is the Hamiltonian? Okay, the Hamiltonian as a function of time will be EM V dot S. Okay, V dot S. Then you just write this whole thing. Copy. I have to make it smaller. And then the spin is dot what? Okay, the spin is h/2 sigma. Okay, sigma. Then you have the sigma is okay, so this is equal to 1/2 sigma, equal to 1/2 sigma. Oh no, sigma x, sigma y, sigma c. Okay, I hope you remember that. And then after you deal with all of this, eventually you get a very simple form. Cosine alpha, negative cosine alpha. I mean, you can deal with the algebra if you're interested. Okay. So eventually you get something like this. And omega 1 will be EB over H bar. Sorry, not over H bar, is over M. So this is the frequency of the the oscillation inside the spin. Okay. Okay, then at every instance, at every time ht, the eigenstate is this. So for every time, I'm not going to prove it, okay? But you just solve this matrix, you get two eigenstates, and these two eigenstates will have this form. This is spin up, and then this is spin down. This is spin down. Okay, and then the energy will be just a minus h1/2. So this is along the instantaneous B field. Spin up, spin down along B, along BT. Okay, for every BT, you have a spin up and spin down. Okay. Okay, so now let's get the Berry curvature. Okay, let's get the Berry phase. Okay, so you can actually exactly solve this and get the Berry phase just by solving the whole thing. Okay, because this is an exactly solvable problem. You can actually calculate how he moved and go back, get the exact solution, and then take the approximation that the time become very long. Then you'll be able to get the Berry phase directly. Okay, this is exactly solvable problem. The solution in the textbook, but because of the time, I'm only going to do it just using the formula of the Berry phase, and that turned out to be a very simple answer. Okay, so suppose the electron is in the spin up state at t equal to 0. So the state is this plus equal to, okay, you just take this one, cosine theta over 2 and E okay, here this theta is just equal to this alpha. I should not use alpha here, but I just follow the textbook. Okay, so you just consider a sphere with the angle like this, theta, phi. Okay. So suppose now you have an arbitrary phase. Okay, so this is the spin up state. Okay, the spin up state. So we are going to do so here, this both depend on time. Okay, because the field is rotating. So this instantaneous state is also rotating. Okay, so now we're going to apply the formula. Let me get the formula. Where's the formula? Oh, here. Okay, this is the formula that we're going to use. We're going to use. Okay, so I think I only need this part. Okay, so let's get this one will be R times in this case it's not just R, it just the just curl is on real space now, okay, because the magnetic field is in real space. Okay, so you have M, then you just do the gradient. This will be the alpha plus, and then this will be the alpha plus, and then this is the area. Okay, so let's get this thing. Okay, you have this eigenstate. So you just get this one. So you just do it according to the spherical coordinate. Sorry, this is this angle. This angle. Okay, so there's no R dependence here. Okay, there's no R dependence. So you just copy this. Basically, you have this dr and 1 over r d theta. Okay, you just do it on every part. The process takes some algebra, but the result turned out to be very simple. Okay, make it more compact. Okay, so first, this thing is 0. There's no R dependence. Then let me just do the derivative on this part. Okay, do it term by term. Then eventually you get something like this. Negative 1/2. I mean, do derivative on here. You get negative 1/2 down. And then you also get a negative 1/2 from here. And then EI. And then we do it from here. The top part give you 0. The top part give you 0. The bottom part just give you I. Okay, so this is this one. And then after that, we're going to calculate this thing. We're going to calculate this thing. Okay, you have to do it step by step. Okay, so how are we going to do it? Let me see. Okay, so this is this one. Copy. And then you need to have a complex conjugate. You have a complex conjugate here. Okay, and then you just times this, dot this whole thing. Okay, you just dot this whole thing. Okay, so eventually, let me see, what are we gonna get? Eventually this part will get canceled out. This part will get 0. And you are only going to get this part. Okay, so eventually the answer is this is 0. Probably we can just calculate it then. 1/2 sine theta over 2 cosine theta 2. Okay, and then plus this one. When this one we cancel, so you get 1/2 sine theta 2 cosine theta 2 and 1 over r. So you get this one, you get this, you get this one, and this one, you get this. Okay, and then and this one is just 0. Okay, so plus this, then you have 1 over r. So this one times this is 0, and this one times this, you get I sine theta over 2 squared. Okay, so eventually you just get I sine theta over 2 squared. Okay, so we get this part. Then the next, a lot of algebra. Okay, just but as a concrete example, I want to do it step by step and just finish it. Okay, then we are going to get this, that curve. And then we're going to get this. Okay, so we're going to use this formula. You're going to get a curve. So here, you go to Wikipedia. Come on. Okay, anyway. Why it doesn't move? Okay, now it is working. You go to Wikipedia and why is it blocking? Okay, anyway, you just search curl in spherical coordinate. Okay, you search for curl in spherical coordinate, and then is this curl? Okay, this is curl. This spherical coordinate. Okay, you're gonna have this definition. Okay, and in our case, we only have the phi components. Okay, we only have the phi components. So you only have this a phi and a phi. So this AR is 0, A theta is 0, A theta is 0, AR is 0. So you only have 2 terms. Okay, you only have this term and you only have this term. So let me just copy it. Okay, so we have r sine theta plus 1r negative dr a theta. Okay, so again, we only have this phi component. So we only have this term and we only have this term. This a theta ar, a theta ar, that's 0. So I copy these 2 terms. Okay, so these are the 2 terms I copied down. Okay, I copied down. So then let's do it. So you're going to have r sine theta d theta. So this one is this. This one is this. Okay, this one is this. Okay, so this one is let me use a color pen. So this is this part. Okay. So we're going to write I and then R. Okay, plus this negative dr r. Of course, this is also here. Then we're going to have I sine 2. Okay, is it negative? Okay, negative. So you'll find that this one, eventually this R will cancel. This R and this R got canceled out. Okay, so you have I sine theta 2 sine theta. And you can see that here, there's no R dependence. So when you do the derivative on R, you get 0. Okay, so eventually you only have one term left. So you're going to get something simpler and simpler. Okay, so you're going to get this term. Okay, you're going to get this term. I forgot to times this. There's a sine theta here. Okay, yeah, it's a parenthesis. There's a parenthesis here. Okay, there's a parenthesis here. Okay, so you can move the I here, I outside. So the R can also move outside. So it will be R squared. Then this thing is just sine theta 2. Okay, so let's continue. We're going to finish it soon. So this one, just use the chain rule, 2 sine theta, and then cosine theta 2, and then 1/2. Okay, and R. So this one is just sine theta. It's just sine theta, and then we get cancel out. So eventually you get 2. Yeah, you get a very simple result. So this is the curl. This is the Berry curvature. This is the Berry curvature. Then we're going to continue. We're going to continue. Okay. So this thing. Copy. Then this is just I, and then times I, 2R dot dA. So this A is the area, okay? And this area is always pointing in the radial direction, okay? So in a sphere, okay? Let's say you have a dA. So how do you get this? Okay, you just, okay. So this is dA. So the dA, this dA is pointing radially. Okay, dA equal to this area, this D area, and pointing radially. So what is this D area? This D area is this solid angle. I mean, it's just, I don't know how to express the solid angle in a. Okay, so this solid angle. Okay, so this is the solid angle, a d solid angle. This is solid angle d times r squared. R squared. Okay, so this is this dA. Then you just continue to write it. This will be negative. Okay, so you have a negative 1/2 1r. So this will be r squared r d solid angle. And then, of course, you're going to do the integration. Okay. Do the integration. Dot. Okay. So r dot r will be 0. This is just 1. This is just 1. So you have 1/2 d solid angle. And then eventually just 1/2 solid angle. Yeah. Okay. So the Berry phase in this process is negative 1/2 of the solid angle. So basically, it means if you have a magnetic field pointing in a certain angle, you rotate it by 1 round, the electron spin is going to pick up a Berry phase 1/2 solid angle, and you can rotate it in arbitrary path, as long as you can rotate it in any path you like. So any path you like, and eventually, you get this solid angle. Any path you like on the sphere, then the electron will pick up a Berry phase. Okay, so that is how we calculate. Basically, let me briefly summarize how you did it. First, okay, first you can consider the Hamiltonian and the main problem, what we're dealing with here. And then you get this eigenstate. Okay, you get this eigenstate. And then from this eigenstate, it depends on some parameters, right? So then you just pick this eigenstate and put it in the appropriate coordinates. And then you just plug into this formula. You just do it. I mean, it's a bit complicated when you have multiple components. You do gradient first, do product first, do curl first, and then you do the integration. I mean, there's some algebra there, and eventually you get a Berry phase. Okay, so you can confirm this by directly solving the Schrodinger equation. Like, don't follow our formula. You just because this Hamiltonian is relatively simple. You can exactly solve it. Just make it move slowly as a function of time. It doesn't need to be slowly. You can solve it as a function of time in any dynamics, because this is an exactly solvable Hamiltonian. You just make it go around. Solve the exact eigenfunction, and then take away the dynamic phase. Then the rest part, the leftover phase, is the Berry phase, and this will turn out to be the same as what we got here. And and what I'm talking to you today is on section. Let me just do it it's on section 10. Okay, so we're in section 10. Section 10 of the book of Griffith, of Introduction to Quantum Mechanics by David Griffith. This is a textbook that people use for undergrad quantum mechanics classes. But I don't think they go into, at least for me, we didn't go into like chapter 10 and learn the Berry phase, but the content is there. And I think the book, I mean, this section, I read it, I feel it's written pretty well. I mean, overall is a nice textbook. Otherwise, it won't be used as a textbook in undergrad. And this part on Berry phase, I mean, I would encourage you, if you have time, you just go and read this section. So in that textbook, there's an exact solution for the spin case. And then you take the exact solution and then take the limits. And then you can get the Berry phase independently. And then you can confirm that this formula is true. Okay, do you have any questions? So far, we haven't talked about any solid state system yet. So later, we are going to apply this concept to solid state system. And then we turn out that there will be interesting effects due to the Berry curvature in solid state system. Okay, any questions? Okay, if no, then we'll end the lecture here. Thank you very much.